My name is Rayees Pasha. I work at Rising Wave Labs. Title of my presentation is Equality Delete Problem in Apache Iceberg. I was told memes do well in the presentation, so this is my cheap attempt to get some laughs. Promise don't have any more memes, but let me jump right into a little bit of introduction about myself first. I lead the product team at Rising Wave Labs. My experience is primarily in the database management technologies, stream processing space. Started out as a developer, and then I moved into product management. I worked on database optimizer for a product called Nonstop SQL. I don't know if anybody knows, but it's a sort of a legacy product from HP, very high performance database. But my recent past has been in more stream processing space, dealing with incremental processing models and how to deal with real-time data in a granular, discrete fashion. In terms of agenda, I'm going to cover 4 things. First, introduction to Rising Wave. We are primarily a streaming database. What's our connection to Iceberg? What our journey has been so far? That's when I'll talk about what we call the concept of open lake. Then obviously the equality deletes problem, which is the topic at hand. I want to give some background about why it's a problem, and then what's our solution look like? How do we handle equality deletes in our own way? And then time permitting, I have a quick demo of what we call NIM table. It's a lightweight manageability tool to manage Iceberg tables. So assuming we have time, we can go over that demo in the end. First, what is Rising Wave, right? For those of you who are not familiar with our product, it's a distributed streaming database. So as the name suggests, it's a distributed system like any other system with separation of compute and storage. But at the heart of it, it's a stream processor. On the compute side, everything is processed incrementally, similar to how Flink and other systems do. But the interface and the query model and the data model is that of a relational database. So it's sort of a hybrid category where you accomplish everything that you do with a regular database, but under the hood, the processing model is incremental. The net result is we can guarantee freshness of data of under 1 second for even complex pipelines, right? So if you look at the diagram, just to walk through how the architecture looks, typically Rising Wave will be sort of the cog in between your upstream data sources, which could be event streams, message queues, CDC streams, typically systems of record that have the original data. And those are the sources for us. And then the downstream systems, the analytical systems, that could be your data warehouses, data lake houses, all of those. And in between Rising Wave is the layer that does the ingestion, processing, and then obviously you can serve the data directly from Rising Wave, or you can deliver it to a downstream system. From a data model perspective, Rising Wave, like I said, it's a relational data model, right? So a stream is nothing but a base table for us. You can join streams just as you join tables through standard SQL. You can filter data using predicates. You can create indexes, views. All the operations that you do typically with a database, you can do it here, except that the data is in motion, right? And once you process the data, you have 2 options. You can store it in Rising Wave itself through our engine. We have a custom-built engine for streaming high-velocity data called Hammock, where we store the data in a raw format, and that's really highly performant for extremely low latency workloads. But the new thing that we added in the last 6 months is support for Iceberg, which is if you want to retain the data longer term in open lake format like Iceberg, you could store the data in Iceberg format. Now, there are differences in how we store the data and what they should be used for. As I mentioned, if you have real-time dashboarding and things where your requirements of latency, data freshness are 50 milliseconds, where there's no human involvement, automatically the data needs to be updated, then obviously Iceberg is not a good fit. You would go with traditional Rising Wave tables. But if you have analytical use cases where you can tolerate freshness guarantees up to a minute or so, then obviously you can store data as Iceberg tables. So my talk will mostly focus on obviously the Iceberg aspect of it, not so much the stream processing part of it. Now, as I mentioned, we started working on Iceberg functionality in the last 6 months or so. over time, we have built a lot of capabilities, right? Our primary goal was to extend Iceberg, which is primarily seen as a batch-oriented ingestion model and processing model, to a more streaming-first approach, right? That required us to build a bunch of capabilities into the product, primarily for Rising Wave users, but also for users who are not non-Rising Wave, but are Iceberg users if they want to use streaming ingestion pipelines, right? So some of the capabilities we have built is automatic compaction. We built a Iceberg compactor, native compactor in Rust, and then we offer a choice of catalog. You can bring in your own catalog, Polaris REST-based catalog or Hive-based catalog. Any of those we provide. And the two things that I really want to highlight that we built for Iceberg are, one, streaming ingestion. You need not batch upload data from Iceberg, but you can also do a streaming ingestion directly into Iceberg tables. That's something we support. And then the support for incremental materialized view. I know in the previous talk, they mentioned about MVs coming, IMVs coming in the next release. In our case, materialized views are a primary interface through which streaming jobs process the data. We have adopted that concept and applied to Iceberg tables. In terms of deployment models, we are pretty open. We support all major clouds and open. There's the open source option. It's an open source project. Basically, it's an Apache 2 license project. So you can try, if you want to try and try for free. Now, in terms of interoperability, we work with all sorts of clouds, and like I mentioned, you can bring in your own storage layer. You can bring in your catalog. So in a way, it's a very truly, truly open source, open free option without any vendor lock-in. Now let me switch gears to the topic at hand, right? So the primary, as you can see, streaming is central to our workflow, right? A lot of the data that we see with our customers is coming in a streaming fashion, either from a message queue or from a database upstream CDC stream. And one of the primary workflows we see is these original data that's residing in upstream OLTP databases like Postgres, MySQL. And users would like to obviously migrate the data from those systems into Iceberg for longer-term retention. Now, the challenge is the way that's done typically is through real-time CDC systems. And we have support for that for Rising Wave system from get-go. But that poses a unique challenge when you move to Iceberg because of the impedance mismatch of how data is written into Iceberg as opposed to other systems that are more suited for high-velocity data. That challenge is basically because of the fact of how you record changes, right? When the changes are made, like when you run IUD operations on primary database, an update basically becomes a delete plus insert. Now, when you implement that delete operation on the writer on the primary database, it's easy because the database is aware of the location of actually where to insert and where to delete. But when that transaction is recorded in a CDC event, that information is missing because in CDC logs only capture the table name, the primary key, and the old and the new values before and after, right? It excludes the physical row location. So the system writer that's reading from that CDC log has to have a way to locate where the exact row is in the downstream system, where to delete, right? And that's a challenge. And different systems handle it in different ways. And basically, Iceberg offers two mechanisms to do that. One is what we called positional deletes. There's another one called equality deletes. They both are different, have pros and cons. They're meant for different reasons. Let me explain first the definition of both, and then we can talk about the trade-off and the actual problem we'll run into with each of them. Position deletes are basically in which, say, if you have to, in the diagram where we have the table, if you have to delete the row 3, right? If you have position delete system, then it will basically record in a file, position delete file, particular row number and the file where that particular row needs to be deleted, right? That's one way of recording a delete and marking it in the table that this row needs to be deleted. And if you're going with the equality delete, we actually reference the actual value. You can reference by the primary key, and in the equality delete file, it actually stores the row's primary key so that you can directly delete the row when you do the scan. Now, position delete is great if you have batch updates where you have bulk updates coming in, you have a lot of deletes. there the cost of the deletes is amortized because you can do a full scan of the table, figure out the exact file path of each and every row, and do the deletes at one shot. But in the case of streaming ingest, what happens is you have sporadic changes coming from time to time. In which case, the approach to do a full table scan to figure out the locations is no longer feasible because every time you have to come and do a random access to figure out which row got affected. So in a way, your position delete is good for batch upload. If you're doing a lot of backfill or you're doing a bulk loading data, and there you have a lot of deletes, it's a great way to address that in Iceberg. But if you have more streaming ingest, equality delete is the way because it doesn't require a full table scan. You actually know the exact value. Now, there is a downside with equality deletes also because each time there is a delete, it creates a delete file, right, that has a specific primary key value of that particular row. Now, if you have a lot of deletes coming in through streaming ingest, there is a proliferation of those delete files. Those have to be cleaned out. So that means extra work on the compactor. So the trade-off is whether you pay the price at the right time or at the read time. And that's the fundamental problem that you have to solve. So it's not a one versus the other approach. So how do you solve that problem? But naturally, from a general comparison perspective, if you have, I will compare why, I'll look at from a write latency perspective, equality delete is low, right? So it's good for CDC use cases. But the same thing on the position delete, if you have a write latency, it is going to be high because you have to do that extra lookup, right? From a query performance perspective on the read side, when you do the merge on read, for equality deletes, the performance is going to be low because you have to keep merging not only your data files, but also the delete files. So as your number of delete files increase over time, your query performance keeps going down. On the other hand, position-wise, it can skip rows, so it can retain that performance. And on the maintenance cost side, with equality deletes, you have to run periodic compactions, right? With position deletes, you don't have to do that because you have very few files to deal with. So in a nutshell, it's like, again, to reemphasize, they are not one versus the other. They are what is good one for versus the other, right? So equality deletes would be good for streaming ingestion, and position delete would be good for batch ingestion. But the challenge is your workloads are never one or the other. You typically have to do both. For any data system, you have to do bulk loads at some point. You will have ongoing real-time updates. So you have to have a system that kind of handles this problem of having to go with one versus the other, right? And that's where our solution comes in, right? The solution we have built takes care of the ingestion path from all the way when you ingest the data to the time when you write into Iceberg. And for that, we have built two separate components that I want to highlight. One is our connector that reads from the upstream source. It's not just a DBZM connector, but it's actually an embedded engine enhanced with some additional capabilities so that it knows how to detect pressure. If there is a sudden spurt of data, it knows how to smoothly take care of the spikes and gracefully handle all this back pressure. And on the compaction side, we have built a purpose-built compactor to deal with small file problem, make it very schedulable so that you can, based on the workload, decide how to do the orchestration with compaction, right? I'll go a little bit more into detail into what the solution encompasses. There's basically three phases to the solution in how we define it. What we call is the write phase, which is basically taking the upstream updates and then writing, right? So here, we know that position deletes or equality deletes, both one of them won't serve. So our approach is a hybrid approach to use a mix of both, right? The second is the compaction phase, where if you go with like equality deletes and if you have a lot of delete files, how do you merge them? How do you make sure that you don't have a problem with thousands and thousands of files accumulating on Iceberg side? And then the third thing is what we call export phase, where even if you maintain those files, how do you make it easy for third-party engines like Snowflake, Redshift, that can read these files and you can query using them. So first problem with high-frequency updates, the challenge is how do you deal with large numbers of delete files, right? Our approach is we basically divide into the updates themselves into two buckets. One is what's called the in-batch updates, where suddenly, say if you have a bulk load of data, so we treat the entire batch as one, and we use position deletes for those. We don't use equality deletes. After those bulk loads are done, when you have ongoing real-time updates, which are much more lower in volume, we use equality deletes, right? That allows us to toggle back and forth between when to use one versus the other, right? The hybrid strategy ensures that you still have the low latency because those smaller updates are still dealt with by equality deletes, so it ensures low latency. But when you have high throughput, we're able to handle it through the position deletes, right? And we avoid random I/O for larger updates. Now, once we handle the right problem, because we have used this hybrid approach, we still are dealt with a lot of delete files. Just because of the nature of streaming workloads, you will end up with a lot of updates that happen all the time, right? So we should be, at the query time, we should be able to have a much smaller set of delete files that we have to read from. Otherwise, there's a high read amplification, right? To avoid that, our compaction service that we built has a lot of smarts. It is a schedulable compaction service. It's based on an Iceberg compaction project. It's an open source project where we are one of the contributors. There's other companies participating to build that. It periodically removes equality delete files based on certain criteria, either on the size, amount of fragmentation in data, by time. So there's different ways you can actually configure it to keep the delete files number low, right? So the way we do that right now is you can fine tune it yourself, or you can define what's called compaction modes. We have what's called a low latency mode. Say, for example, if you have a particular workload that requires data freshness guarantees of 1 minute or maybe 2-3 minutes, you really turn it on so that the compactor is aggressive in terms of merging and getting rid of those delete files. What's this offline analytics mode? Say you have a workload where you say, I don't care, the freshness can be up to 15 minutes or maybe an hour. Then you turn on that mode that automatically will tune the compactor to use less resources and less frequent compaction, right? Because it'll create I/O storms. Otherwise, you'll have a lot of file creation and file churn. And we also have other future optimizations like partial compaction, ability to handle larger compaction sizes. Those are all part of the roadmap. And then the last phase is the export phase, right? We did all this to create, you still have equality delete files, but fewer in option, right? One of the challenges with this approach of position file, delete files and equality delete files is that some of the query engines don't support equality delete files. Like, for example, Snowflake, Databricks, and Redshift, they only support where the deletes have been handled through positional deletes. And for those, we need to provide a clean version of the data. So for that, our solution is to have a one-off compaction job that you can run, which goes ahead and removes all of the delete files altogether and creates a clean version of the Iceberg table so that they can be queried right away, right? So we believe this dual path advantage is a good way to de-risk yourself. I know version 3 of Iceberg is bringing deletion vectors. That'll probably solve this problem to a large extent, but in the interim, this is the approach that we are recommending. We have a customer. Actually, the reason why we did this is not because of the academic exercise. We actually have a customer, Siemens. They use SQL Server and Snowflake, and they ran into this problem where they had this workflow where they were bringing data from their upstream OLTP database to Snowflake. Everything was working great. They wanted to move to Iceberg. And then once they moved to Iceberg, they realized that the streaming ingest would create equality files, and Snowflake wouldn't read that. So they had to write a custom Spark job to run periodic compactions. So that created a lot of problem, and then they had to obviously pay for the cost, latency, and having to manage 3 different systems. So that's when we came in and we figured out this hybrid approach, and obviously we lowered the cost and data freshness guarantees, multiple things that came out of this project. And so we thought we could share this with the community and see this is an option. This is a way to address this problem. So I want to make sure that I can show the demo. So maybe I can pause here for a second to see if there are any questions, because the next topic is a little different. Yeah, hi.
The export for...
He needs to bring the mic, I think.
Sorry,
Yeah.
I have to bring the mic for the camera. There we go.
The export you mentioned for Snowflake, how often does it run?
They have a daily job. We told them you can make it hourly, because the Spark, it was a daily job. So they had to wait for the entire day and then run the Spark job, and then they would produce the result. In our case, they do a daily, hourly job. So at every hour, they have a cadence, scheduled compaction job that kicks off and creates that clean version.
Did you consider doing some kind of indexing in order to just write positional deletes in the stream?
I would have to check with engineering, but I think, as far as I know, the streaming the positional deletes was not an option because of the volume of deletes that were there. Because it was becoming impractical because this was a large customer with lots and lots of data, in thousands of updates, so it just became hard.
Here you go.
A couple of questions. One is for the exports to external engines. You're basically maintaining like a second copy of the entire data set, or is it something else?
So it'll be a single copy only, because when you run the compaction job, special job, it will auto remove the delete files, and it'll have the same single copy of Iceberg tables.
Right, but like, how do you maintain two versions? One readable by Iceberg that is compacted, and another one that's real time.
Yeah. So in this case, there was only one copy because it was just for Siemens. But if you have, say, two separate workloads, one you want to keep it like low latency,
right,
and the other one more analytical, then you obviously will have to maintain two copies. In that case, like I mentioned previously, you could as well go with a rising wave table for like ultra low latency, and then Iceberg for all your analytics.
Second question is about compaction. So like you said, your customer was rewriting all the tables. So as part of compaction, are you doing the same kind of compaction where you rewrite all the files? So for example, I don't know, like there was a record like 3 days ago, and we just updated it. Like, do you have to rewrite the same way all files, or is your compaction basically converting converting quality to positional deletes?
The compactor has some multiple levels that it does. So I have to check with the team, like if the entire table needs to be rewritten, or is the size of the file, because there are some tuning parameters in terms of how large you want to keep those files at, right? That will determine whether it triggers another compaction, or we can live with that positional file there.
Okay, thank you.
So how do you handle the source like being impacted during full load especially?
How do I
handle the source load during full load? So how is, like, do you apply back pressure that the source is not being impacted and all?
Good job.
So,
good question. So with the Debezium connector we have has some sense, like intelligence built in, that looks at the throughput and sees what the compute capacity, and it has ways to buffer the data so that if there's a sudden spike, so it doesn't overwhelm the rest of the system, not just in the processing layer, but also further down on the compaction side. Because if you have under-provisioned your compactor resources, that will back up everything. So there is a way to know, okay, I see a lag. We have something called barrier latency that keeps track of how much lag I have in terms of upstream processing. And based on that, we will say, okay, I can't take any more data, because that's an inbuilt mechanism we have.
So is there any hard limit that you stop, like the source not being impacted more than 5% or something?
Yeah, it basically, you will see that the barrier latency keeps going up and up and up, which means that it can no longer process data, right? So your data freshness will fall through the fall off the ground, right? And then if it's so extreme, it might run out of memory, basically. So the first thing is the performance will suffer, freshness will suffer, and the last phase is basically your cluster will get host in worst case scenario. Yeah.
Thank you.
Okay. I have 3 minutes. Can I go a little over, or do you? Yeah.
I think
okay.
you'll be okay to go a little over since you already took Q&A.
Okay. So Nimtable is a new project. We as part of our Iceberg rollout, we worked on. It's an open source project. It's a very lightweight manageability tool to manage Iceberg tables. Some of the functionality that we include is Visual Catalog Explorer, so you can look at the catalog, look at the objects, look at metadata and do some sample querying if you want to. It also provides some basic access control on the tables themselves. And if you want to tag and see lineage of the data, of how the data moved to Iceberg, some of the capabilities are there. So I'm going to try and do a quick, I can just showcase, show the thing if you, I'm running it on my system. It's connected to a catalog. So I'm just going to, okay, so you can see my screen. So this is the landing page overview. So on the dashboard, it will show you the recent activity. So this is sort of your front end for all of the compaction, any lifecycle management tasks that you do on your Iceberg tables. So it will show you the recent activity in terms of what you ran. It will list you, from the catalog side, it will show you all the catalogs you're running. In this case, I have a catalog that I've already connected. It's running on S3 tables. But you can also import, you can have multiple catalogs. This is a single solution to manage, if you have multiple Iceberg instances running, you can connect through single interface, right? So here you can import, you can connect to a new catalog using different ways. If you have a REST catalog, or if you have JDBC catalog, S3 tables, or you can load it from a config parameter. So there's multiple ways you can bring in. So in this case, I've already, as I said, have a catalog running. So I'm going to go there. And if you can click, that will show you the namespaces that are there. And I have one particular namespace that has tables. So I can go navigate to the tables. And I can, let me go to a sample table T1. It will show you the metadata of what the table looks like, how many files are there, what's the size of the table, how many records are there. In fact, here it will show you in real time, if I had some data flowing, it will show you how many position deletes I have, how many equal deletes I have. It will also show you the different file sizes distributed by what the file size of each of them are. You can look at a quick data preview. It will show you the sample data. It will query the Iceberg table and bring the data. It's probably taking a little bit of time. Yeah, so you can show you the simple schema, some sample data. You can also look at the version control. If you have multiple versions of the table, if you have multiple snapshots, it will show you when those snapshots were created so that you can see how the data has changed over time. Let me see. You can do basic SQL querying. It's like a regular SQL client embedded as part of the product. And then there's this part is more admin stuff. Like here is the actual optimization. Like for example, if a particular table needs to be run compaction because it's unhealthy, you can click optimize to run automatic compaction. And you can also schedule compaction tasks. Like for example, if, as I mentioned in the presentation, it's a schedulable compactor based on your workload, so you can have predetermined criteria of how you want to manage those Iceberg tables. Yeah, and then there is a cool AI bot that you can use to answer questions on your Iceberg. It's called Nimtable Copilot. So you can ask any questions and it'll retrieve answers for you. If you're playing with the tables to figure out what the data looks like, what does the schema look like, all of those capabilities are built in. As I mentioned, this is not a standalone product. This is just a sort of accompaniment to our efforts on the Iceberg side, but they are not meant for only Rising Wave Open Lake. Even if you don't use Rising Wave, you can still go, it's an open source product. You can, if you're running on your own Iceberg, you can just use it to manage as a lightweight tool. So that's pretty much it. I think we covered the questions, and I think back to the summary, deletes are a problem in Iceberg. I think as I showed you, they're essential but tricky. There's trade-offs between position and equality deletes, and there's inconsistent engine support, especially on the equality delete side. So our hybrid approach, I feel, is one way to address that problem. Any final questions?
All right, really quick questions, really quick.
Okay. For the rising wave for on the compaction, before you expose to the external catalog or external engine, the compaction only converts the equal delete into the persistent delete, or you will do a real compaction, for example, rewrite the files?
So if I understand the question, before we do the export, do we handle equality deletes or positional deletes? So in our case, the positional deletes will remain as they're smaller. The main problem the compactor would do is reduce the number of equality delete files and merge them as much as possible to as small a number as possible before the export phase. And when you have to do the export phase, you have to completely eliminate them, especially for query engines, right? That's when you run that step to basically provide a clean version with no delete files.
Okay, thank you.
Yeah. All right, thank you, everyone. Oh, okay.
Sorry. In the NIM table example, I was curious what the heuristics that you use for like needs optimized versus not needs optimized, because you had a little green label there. I'm just curious, like, what do you guys evaluate?
So there is some inbuilt criteria about the fragmentation in data. Like if your table size is X, if there are so many files, if the average the file size of the Parquet files is below a certain threshold, it automatically triggers. That's when it doesn't even trigger, it tells you that the table is unhealthy, which basically tells you to go ahead and take care of some action. Yeah. All right, thank you, everyone.
All right, thank you so much.